Hi, this is a video of the alloy analyzing capabilities of the Thermoscientific Niton XL2 Plus analyzer. One of the nice features is a grill protection for the detector. You can see that carbon fiber grill that protects the detector from sharp metal punctures that make it past that thin plastic window there. That's probably the most common repair that there is. So if we can eliminate that from happening, that's a good thing for our customers. I'm going to show you the camera. A little challenge holding the camera and the analyzer at the same time. So it has an embedded camera, so when you do an analysis, if you want to stay away from holes or hit the ground spot, you're using the camera to help guide you. Say, oh, there's the hole. I need to get on the metal part and do the scan. This is 316 stainless. So what we're doing ideally is listening for the beep, watching for a single alloy showing up, and that it be green or blue, which are good or excellent matches. The number beside excellent, that's 0.2, is a match quality number. We'd like that to be below 2.0. That will tell you it's a good enough match. The lower the number, the better. Anything below 1.5 is a very good match. So the next sample is going to be 304 stainless. Okay. I saw a couple of other alloys show up. So whenever you see two alloys or things changing up there, you just give it a little bit more time for the analyzer to sort of focus in on one alloy. This one is 321 stainless. Next is Niton XL2. This is Niton XL718. Next is alloy 42, it's a high nickel. Oh, I think I missed the sample. Sorry. It's an example of not using the camera. So I'm going to line up the line for smaller samples. We'll talk about smaller samples a little bit more later on. There we go. Next one is stainless 430/440. Can't tell the difference between 430 and 440 because the only difference is carbon level, and XRF technology cannot see carbon. This next sample is pure tantalum. Pure elements can be a challenge with XRF because they kind of flood the detector in the spectral area and make it difficult to see. But we have no problem with pure tantalum. CP just means commercially pure. This is titanium 6242. Next sample, we're getting into a couple of copper-based alloys. This is a CDA 360 free cutting brass. Next sample is a beryllium copper. Samples don't have to be flat. XRF technology cannot see beryllium, but what it does see is a little bit of cobalt that is always in beryllium coppers, and that's how it identifies it as a beryllium copper CDA 172. The sample is copper with a little bit of iron in it. It's 194. We got some low alloy steels. This is a 4340. This is a 4130, which is very close to 4140. You might see 4140 pop up here as well. I'm going to do that one more time. I would like to get a blue or a green screen on that one. There we go. So we've got some tool steels now. So this is the one's an M2. It's a little bit more of a challenge because of the size. Let's see how well I did. Okay, we'll do one more so I can keep that blue or green screen there. There we go. This next is an M4. We've got a T15. My number's good enough, but I would like it to be better. Oh, there, we finally got it. There's a good match. Now this one is a very small sample. This is a 15.5/17.4. For really small samples that are much smaller than the window of the analyzer, if I just put that on the table, it's going to analyze the metal and the table. It'll see some of the elements that are in the table. If you put it on styrofoam, styrofoam is invisible to the analyzer, so this is a great way to do smaller parts. And so first of all, I will line it up with, I'll try to line up the metal, and then I'm going to use the camera to kind of, whoops, not quite there, get it in the camera. That's a nice shot. 15.4, 17.5, those have overlapping chemistries. 15.5. Now we're going to move on to some aluminum alloys. This first one is 6063. $60.61. $1100. They're 3003. We might see 3004 show up also. If 3000 series is good enough, that's great. Give a little bit more time and it would settle on 3003. Last one, oh, this one is 7075. Two alloys, both 7075. Okay. This one is 2024. So what you'll see is a match for 2024 and 2014. If you want to know, again, is it specifically 24 or 14, give it more time. And then something's going to go away. And it'll settle on 2024. This last one is probably one of the most difficult aluminum alloys I can find. It's 5454, and it's so close to some other 5000 series alloys. And this is probably about the longest scan that that I could come up with. So you'll see different alloys popping up. It's sort of like a 3000, sort of like a 5000, but give it time. Things are changing, and then it settles in 5454. The last one is a sample of zirconium 702 that doesn't have good chemistry. So when something has poor chemistry, what you'll not hear is a beep. It'll say possible match. You see my number's high at 2.2, and the iron is in red, which means, you know, this is not really a good match for this alloy. So what we can do is tap on the line of the alloy and it pulls up a different screen, which is the library for zirconium 702. So the library entry, the minimum and maximum specs for zirconium 702, and the middle column is what it measured. And if you scroll down looking for things in red, there's not supposed to be any iron, and the minimum is 0, the maximum is 0, and it's seen about 1%. That's what's throwing the alloy match off. Everything else is within spec. There's a little bit of a residual tin there, but not enough to throw off the alloy match. So what this sample is, it was shot blasted with iron pellets. So it embedded some of the iron in there. When I grind it and clean up the metal and then shoot it, beautiful match for zirconium 702, and the iron went away. That's the importance of, that almost went away. That's the importance of sample cleanliness. Thank you for watching. Bye-bye.